Learning objectives in this lab, you will first see how charge can be separated and transported to metal conducting balls. Then you'll measure the force between those, and we're going to measure the force, see how the force depends on how much charge is on, and how the force depends on the distance between charge. So that's what we've been doing the first week of class, looking at Coulomb's force law. This is Testerson. You'll have your own name here. Okay, so some things to know about electrical charge. We have both positive and negative charges. You know this from chapter 20. Opposites attract, like charges repel. We'll see that today. Materials in which charge easily flows are called conductors. Things like metals, rubber, glass are called insulators. Charge does not easily move around. It's just based on the structure of the materials. Okay, so what we generally refer to as static electricity occurs when an object gets excess charge. Either it gains electrons or it loses electrons. Electrons are the charge carriers that we have. Okay, so we could rub things together and move electrons around, either add electrons or remove electrons. So this is what it'll look like to you. Charge carrier on electrophorus. So the video shows how electric charge can be transported to the conducting metal balls that will be used to study force with this device. So here's fur. We could use this to charge things up. Here's a little link here if you want more information. You can click on that. So animal fur rubbed on this foam, and you'll see that in just a minute, strips negative charge off the fur. So when you rub the fur on the foam, some electrons are left on the foam, and then we can use that to do some charging. Let's just watch the video first, maybe. So there's a couple of metal conducting balls here. This is actually measuring force. So I can hit play. Negatively charging up the foam. You touch the conductor there. Now notice the person's about to touch the disc here. When the person touches the disc, the person is grounding the disc and bleeding electrons away from the disc when that happens. So grounding means literally the person is touching the ground. You have a path for electrons to move. Although you're not a great conductor, you are able to conduct some electricity. So at that point, what happens here is after you charge up the foam, it's negatively charged. You touch the disc to the foam. Now, because of the shape of the foam, it's not completely flat. Charge doesn't easily move on to the metal. Some of it does, but not a lot. What you do get, though, is a separation of charge. So at this point, let me go back actually, so you can grab this and move it around. So at this point, the foam is negatively charged. The disc is sitting here. Electrons can't easily move from the foam to the metal, though, just because of the shape of the foam. But that drives electrons to the top part of the disc, leaving the bottom part positively charged. So once the person touches the disc, which you'll see in just a second. Maybe I passed it up. Yep, I passed it up. Once the person touches the disc anyway, electrons are free to leave the disc to ground, so that leaves the disc positively charged. Okay, and that's sort of spelled out here in all these different numbers 1 through 4. Okay, so that's a way of making the disc positively charged. Okay, very good. There's also a way to make the disc negatively charged by something called induction, and we'll see that as well. So let me go to the next section here. So the positively charged disc can be used to remove negative charge from the conducting balls. Remember, the disc is positively charged, so if you touch one of the conducting balls, this one or this one, you can, because it's positively charged, you can remove electrons from it. Okay. Okay, so it can also be used to put negative charge on the ball, something called induction. So the way that that works is, I mean, if I directly take the disc and touch it, electrons move from the ball to the disc, making the ball positively charged. I could also take the disc, move it close to the ball. Because this is positively charged, negative charge moves to one side. I can touch this conducting ball, and electrons will flow from ground up to here, because remember, one side's positive, one side's negative, making the conducting ball negative then. Okay, and that's again spelled out here as well. So we're going to be using these ideas to charge up these conducting balls. We'll use the disc to make the balls either positively or negatively charged. Okay, here you can kind of change whatever you want to change. Click here. So bringing them into contact. Remember, contact means positively charged. So contact is positively charged. Induction means negatively charged. Okay, and you can change these around if you just click on it. Now that's induction. That's the bottom sphere. That's the top sphere. Load. It's a different video then. Okay, so you'll have to play around with that. And actually, everything I'm saying is pretty much in these different suggestions here. So remember, contact means positive charge, and induction means negative charge. Okay, so then watch both videos where the spheres have the same charge. And is the force repulsive or attractive? And it tells you here in the text what that means. So the spheres are charged either with the same charge or opposite charge, and the scale reads positive if the force is downward, and negative if the force is upward. So that's the force on this one, the lower one. So if it reads positive, the force is down. That would, I don't want to say too much. If the force on the probe in the meter here is negative, that means the force is up. Okay, I don't want to say too much about that. Okay, so explain your reasoning. Same thing, watch both videos where they have opposite charge, and is it attractive or repulsive? Okay, next part, force and quantity of charge. So you have a little tool kit here. Here's a ruler that you can use. I don't think you don't actually need it for this one. In this video, you'll see how the force between the two charges depends on the amount of charge as the charge is changed. So as you see in the video, two conducting spheres are given the same charge, and the force between them is measured. Another metal sphere is then brought in contact with the lower sphere. Since like charges repel, the charge on the fixed sphere spreads out, and some moves on to the other sphere, the one that touches it, resulting in the force being cut in half. So let me show you this. Charged up, and you could read the amount of force on the force probe, 0.00154 newtons. Now the person is going to touch the sphere with this device over here, and it's going to cut the amount of charge in half from the original amount. Let's watch it. Okay, so by touching it, we're taking some of the charge away, and the force is actually cut in half. So this one has half as much charge. If you know Coulomb's force law, that shouldn't be surprising, because the force is proportional to the amount of charge. Do it again, cut in half again, approximately, and so on. So you've got to take that data and put it in the data table. And here's the data table. So okay, watch either trial 2 or 3 and put the data here, not from trial 1. And how do you change the trials? Do this, and then trial 2, load, go through the same thing that we just watched. So how would you actually enter that? I'm just going to make up a number here. So let's just say the force was, when it was completely charged, 1. Now, when you touch it the first time, you cut the charge in half, so this ratio is 0.5, and then the force changes. I'll just say it's 0.5. Again, I'm just making up these numbers. Now, when you touch it again, the charge is cut in half again, so we've got 0.25 of the original amount. This means charge per original charge. And then I'm just going to make up some numbers here. I'm making mine too good, actually. And you probably will have more data than this. I'm just doing 3 just to show you how you can graph this then. Okay, if you need to add more rows, you just click here, insert row below, for example, if you needed more. Now we're going to graph this. You know, if we were doing this in class, we would be using Excel. Luckily, this program has some pretty good graphing capabilities. So let me plot here force. I'm not going to include any uncertainties. So I just clicked on the actual axis label here. I could do the same thing here. Charge ratio. I'm not going to put any uncertainties there either. And there's my data. Again, you'll have more than that. The title is supplied for us. Now I can include the best fit line here. So let's just go through this real quick. To plot a graph of your data, click on the titles. That's what I did. These are the axis titles. And we could use the gear icon to do a curve fit. So curve fit. Right now there's none. Here's directly proportional. So that looks pretty good. I can change this around, and you can tell how good it is by this fit parameter here. The RMS value, 0.019. Let's compare that to, say, curve fit linear. .0241, so I think it was better before. You can try some other ones. You know, maybe for some reason you think it might be square law ratio, or, you know, curve fit. So there's the best fit line, and you can see the RMSE value is really big. So when this is the smallest, that means that's the best curve fit. And you can tell by looking too, does it go through the points. So I'm going to go back to this curve fit. This is actually the one that works the best. I think that was the best one anyway, yep. Okay, so which curve fit is best? I'll leave that to you once you get your data. Okay, good. Force versus distance then. This one will actually have to use the this ruler. So I've clicked this gear icon, it opens up the ruler, click it again. There's the actual meter stick. This is in centimeters. Notice the 0 mark is not at the edge, it's right here. So I can measure the distance between these. Right now it's about 42 centimeters or 0.42 meters. And I can change whatever video I'm watching. Positive, 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 negative, 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 etc. Just put cancel because I'll just use that one. First, pick one of the 2 videos that use the same charge. Okay, positive, positive, that would be one of them. And you can click change to bring up other ones. Which one did you watch? Okay, that's an easy point. Positive, positive. Measure the distance between them, and then convert to meters, and then measure the force reading. So you're gonna have to hit play. So in this one, we're leaving the charge the same, we're changing the distance, and we're going to see how that affects the force. Okay, so there's the force. So I hit pause, I can write down the force in my data table, distance and force. Now I'll hit play. They're changing the distance. Whoop. Okay, so with this distance, here's the force, and you can get several other ones. There's the force. Force is getting bigger as the distance is getting smaller. Okay, so get several different data points for that. Put that in this table. You probably have to add a couple of more rows here. And then same thing, I'm not going to go through all of this since we just did it. You know, whatever you want to plot here, I would put force here, distance between them here. Okay, very good. And then the title will be automatically populated once you do that. And then you have to go through and figure out which curve fit works the best. Hint, it's not going to be linear. It shouldn't be if you think about how the force is related to the distance between the charges in Coulomb's force law. Okay, and you can tell visually, you know, which one goes through the points the best. You could look at the RMSE values as well. Okay, and then go through the rest of them here, opposite charges, etc. Okay, so you have another graph here. Okay, so go back through these and answer the questions. I don't want to give too much information away. Yeah, I won't say it too much more about that. There's something called the linear fit parameter that you can see. Let me go back to the graph I actually made. Where do you get that at? Well, it's right here under all this information. Okay, so when you make the graphs down here, you'll have the same thing. So when it refers to the linear fit parameter, that'll be underneath your graph. Okay? How many electrons? So compare your best fit curves to Coulomb's law. So in class, we have an R squared here. They're just using D squared. It's the same thing, they're just calling it D. Here's the constant that we had before. Here's the fundamental charge. So F is equal to K Q1 Q2 over D squared. And then from the graph, F is equal to, you'll see once you do the graph, A over D squared. A is some constant. Now if you compare these formulas, A has to be KQ squared. Okay? So you can solve for Q that way. So this first part is Coulomb's force law. This part is from the graph. They're both force, so you could set them equal to each other. There's a D squared and a D squared, so we end up with KQ squared is equal to A, and then you can solve for Q. So you have to use the A from your graph, divide it by K, take the square root. That'll give you the amount of actual charge on the spheres, and if you know the amount of charge, then you can figure out how many actual electrons that you have, right? Because you know the charge for one electron. All right, good. Any questions, email me, and when you finish the whole thing, put submit for grading. Now, if you don't have to finish it all at one time, you could do save progress, and you come back and work on it later. Once you hit submit for grading, it doesn't allow you to go back and work on it anymore, though. Okay. All right. Again, any questions, email me, and I'll talk to you soon. Bye-bye.